Hello everyone and welcome to another video. So today I want to talk about one of the most simple ways you can implement a control system, and that's using what is known as an open loop control system. This particular case I want to look at is implementing something using lookup tables. Later on down the road we will look at more sophisticated open loop control systems like feed forward control, but for this particular discussion I want to start real simple and talk about this idea of lookup tables. The idea is really simple, and I think the easiest way to set the stage for that is to consider a system which is pretty simple, single input, single output, kind of a slower dynamics, longer time scale system. Let's look at this thermal system. So remember we developed in several previous videos this system here, which is nothing more than a heater and a temperature sensor, right? So it's basically a really simple thermal system which kind of acts like a first order system with a little bit of time delay. It doesn't really matter what this system is. The techniques we're going to talk about today apply to pretty much anything. So let's abstract this. Again, the thermal system that we're interested in, it's just some plant where we talked about this earlier. The inputs to this is a control signal U that is 0 means turn the heater off, 1 means turn the heater full blast on and try to heat this thing up as fast as possible. Really what this is implementing is it's changing the duty cycle to a PWM signal going to the heater, but for our purposes all you want to think about this signal, it's 0 to 1 in some continuous fashion, okay? The response of this system then is just some temperature, right? There's a thermocouple inside of it, and when you turn on the heater, the temperature rises or falls depending on what duty cycle it is. And that's all the system is, right? Single input, single output. It's pretty simple. And now what we want to do is we want to be able to control this system and say, how can I get the output to be some signal or some value that I care about, okay? So the easiest way to go about this is to do sort of a dumb brute force approach to this. What I mean by that is, let's do something really simple, like, for example, on the input duty cycle, let's just start with some very simple test signals. For example, why don't I put in a duty cycle of 1? So I'm just going to start at 0, 0, 0, and then at some time I'm just going to step the input up to 1 and hold it steady, okay? That's about the dumbest thing you can do with your system, right? It's just set the input control signal to some constant. Well, what's the output going to do? The output is probably going to be, okay, it's going to be sitting here probably at some ambient temperature, right? Maybe 22 degrees Celsius. And then when you turn on the heater, it's just going to start rising, right? And it's going to do something like this probably, right? And what you can probably find is you can find out what is the steady state temperature that you reach if you apply a constant 1 duty cycle, full power, turn the heater on as much as you can. Right? Okay, so you get that response. And then as you can probably imagine, the next thing you might want to do is, okay, instead of turning this thing on full blast, what if I go ahead and turn this on to like 80% or 0.8, right? And just hold it constant, okay? Well, the system's going to probably do something similar, right? It might be here, but then it might not come that high, right? It might not get as hot. All right. And again, this is nothing fancy, so I'm not going to belabor this point. In fact, I went ahead and gathered some data for this system. Here's a plot of what this looks like. And as you can see, I should shut up right now because this is simple, right? You put in a whole bunch of different inputs, you read a whole bunch of different outputs, and really what we care about in this point is I really want to know what is the steady state response. So I'm going to look at what are the values at time as time goes to infinity or a long time, right? So I can easily tabulate those data. That's what I've done right here. I've gone ahead and made myself a table of the control input or the duty cycle, right? This is the U. This is the input to the system, okay? And now what I care about is what is the output at steady state. Okay, so you can see here when you just do nothing, 23.8 Celsius. When you turn the heater on 20%, the steady state temperature rises to 36 degrees, et cetera, all the way can get as hot up to 69.2 degrees if you turn the heater completely on, right? So you've gone ahead and made yourself a real simple table. Right? Would you agree? And in this table, this embeds information about the plant, right? About this system dynamics, right? To some degree. You understand almost like the DC gain of this system, right? If you put in a constant value, what's the constant value you're going to get out at the end of the day, right? If you let time go on, right? Okay, so you can easily put this in a table. correct? Does everyone agree? I can put the duty cycle on the x-axis, I can put the steady state temperature on the y-axis, and I can make this data, right? I basically just take all this data, put it into here. Would everyone agree? That seems totally reasonable. Well, this is saying, right, you stick in a duty cycle, this spits out the steady state temperature that you achieve, right? Why don't we invert that table in the sense that, why don't I just switch the axes, right? So instead, let's go ahead and I'm going to draw a big arrow and just say invert table, which really is just fancy ways for saying, like I said, switch the x and the y axes. So now on the x-axis, you have the steady state temperature, and on the y-axis, you have the duty cycle. It's the same information, but now you can think about this as now saying, I now have information about if I put in a desired temperature, like how hot do I want to get, I can now read off what duty cycle do I need to achieve this desired temperature. Okay, so what that means from a block diagram perspective is, let me erase some of these, all right? What you could do is we're effectively inverting the steady state behavior of this plant. Maybe I'll draw this in blue, but you can now think about having a block right here, right, where you implement this inverted table, right? So what that means is what comes in to the input, this is the desired steady state temperature in degrees Celsius, and what comes out is the duty cycle, correct? And that's exactly what we want to do, because then we can hook this up to this system, right? So all this is what we're going to refer to as our open loop controller. Because this thing is really stupid. All this thing implements is basically this lookup table right here. So inside here, all you need is some kind of function where you put in the temperature in Celsius on the x-axis, and what this spits out is the duty cycle, U, on the y-axis. And it's basically that table exactly, right? So all you need to do is just make this table. That's all this is. So your open loop controller is really simple. All this thing is, it's basically, like I said, inverting the DC gain behavior of the system and sticking it in, right? So that's pretty much it. In fact, why don't we jump over to Simulink and I'll show you how I built this real system in Simulink and hooked it up to an Arduino to actually have it control the heater, and we can actually gather some real data here. All right, so here's a Simulink model of that thermal system that I talked about, and now's maybe a great time to mention and remind everyone that if you're interested in any of the code here or any of these Simulink models or the lecture notes, check out the description of this video. There's a link there that will take you to my GitHub page where you can get those lecture notes, and in this case you can get the Simulink model right here, as well as any other code necessary to run this, so you can follow along if you like. I'll quickly just walk you through this. The plant is the thing that's probably of most interest at this point. The plant, it's the same plant model that we derived in our previous videos where we talked about how to basically go around and control a system using an Arduino and Simulink. So you can see the duty cycle signal comes in here, and that gets sent to a PWM channel on the Arduino, and again that is hooked up to a MOSFET which controls the 5-volt power supply going to the heater. And then we've got a thermocouple max 31856 unit that I programmed up and have this thing basically talking to all the registers. And at the end of the day, you know, again, we have a dedicated video talking about how to set this up, but what we mostly care about is, again, we can abstract and just remember that this is just reading the thermocouple and getting us the temperature of the thermocouple in degrees Celsius. So again, at the highest top level, it's a single input, single output system, right? The duty cycle goes in here, the temperature of the thermocouple comes out here, and now all we're going to do is, well, actually, maybe let's talk about this little switch here before we get to it. This switch, I just use this sometimes when it's in the down position. I can then just go ahead and manually input duty cycle commands. And in fact, that's exactly how I generated these plots, right, that we flashed up on the board earlier. I just manually put in, you know, a duty cycle of 1, that gets you this top curve, duty cycle of 80% gets you this middle curve, etc., etc. And we use this, just like we talked about earlier, to basically go ahead and build the open loop controller. So this here, if you look and I go under the hood, it's just a simple 1D table in Simulink. It's really simple. that this guy, all it does is it basically, oops, sorry, let me bring that up, right, has duty cycle on the x-axis and the temperature on the y-axis. Or sorry, excuse me, I said that backwards. It's got temperature on the x-axis, right, and the duty cycle, or the table data, is on the y-axis here. So again, all that is basically implementing is this table here. Right, so yeah, it's just all that data. And in fact, you can even kind of see the nice thing about these 1D lookup tables in Simulink, because it tries to draw it, and you can kind of see it does look like the actual data. So again, you see that if you want a temperature of, oh, say, I don't know, 36 degrees, you need a duty cycle of 0.2, and if you want something, I don't know, in between these tables, they can interpolate between actual data points. So in this case, we are just using linear interpolation, it looks like. So again, just to drive that point home, if you want a temperature like right here, like 50 degrees, that's not an actual data point, but that table in Simulink, it should interpolate us and get us a duty cycle of, I don't know, a little less than 50%. Should hopefully get us a temperature of 50 degrees Celsius. So anyway, that's what this is doing. So again, the Simulink model is pretty darn simple. And I will point out the reason it's called open loop, right, is if you look at this, the temperature measurement, it's not being fed back. The controller is not using any of that information. All we're doing is we're sending in a series of commanded or desired commanded temperatures, and the lookup table is then basically finding what is the control signal you need to achieve this at steady state. So let's go ahead. I'll hook up the actual real system. You can see it here in the picture-in-picture. And what we can now do is basically just run this. So I'm going to go ahead. I'll set it up. I'll hit monitor and tune. And we'll run this and we'll go ahead and get some data. So let's do that. And it's a pretty slow process. So instead of watching it, I'll just go ahead and hit play. And we'll come back and I'll show you the data when this is done. Alright, so here we are 15 minutes later. So let's talk through what we did during that test. So you see it started here at a desired temperature of 0 for I guess 5 seconds, and then I said, okay, make the thing 45 degrees. So the blue is the reference temperature, and as you can see, this worked surprisingly well, right? At 45 degrees, the open loop table just looked it up and interpolated and said, okay, it looks like you need a duty cycle of about 37% in order to achieve that. So that's what it did. It turned on the heater at 37% duty cycle, and look at this, it was getting there. And then at 300 seconds we actually said, okay, instead of 45 degrees, let's step it down to 40 degrees. The duty cycle lookup table did the right thing. It looked up a lower duty cycle of, in this case, 27 degrees, and as you can see, the system started cooling down and getting pretty close. And then again, lastly, at 600 seconds we stepped it up and said, okay, I now want you to get hot all the way up to 50 degrees Celsius. And again, the system responded, and check this out. This is not actually too bad, especially for no feedback whatsoever. I mean, if you zoom in on this, you can definitely see, I mean, there's some error, there's some steady state error. It doesn't look like it's nailing it exactly, but this is not too shabby, especially for something so simple, right? Now, the place where this is going to fall apart is what happens if the system is not perfect. Okay, so what we're going to do is, in fact, I'll show you in the little picture-in-picture. Now, let's repeat this exact same run, except now what I'm going to do is I'm going to turn on this little fan, and I'm going to blow this little fan and introduce a little breeze over the heater. Okay, and now let's rerun this. I'll run this exact same experiment again with the fan on, and let's see what ends up happening. So again, this is going to take another 15 minutes to run, but let's do that, and we'll come back. Alright, we're back, so let's take a look at the results, and let me pull this up, and you can see this is not great at all. In fact, if we compare the two, one next to the other, in fact, let me see if I can put these on two separate screens. There we go. So the left is the original system, right, where everything was perfect, and the right is now when we had the fan on. Now you can clearly see this is not doing great at all, and in fact this is the one major problem with these open loop control systems is, in fact, it does not respond or adapt to changing conditions. What do we mean by that? If you look at the control signal down here, the command, right, the U signal, again, remember, the actual temperature was not fed back. So this controller is doing the exact same thing every single time, irrespective of what the actual plant is doing. So even if there are disturbances that are changing the plant dynamics or affecting something, this open loop controller does the exact same thing every single time. And you can see that by looking at these two traces of the control signal U, they're identical. And now we see the consequence, right? On the left, when everything was perfect, when the plant was acting nicely, there were no disturbances, this open loop control system did reasonable. But now on the right, when we have the fan on, it's way, way, way off, right? It's kind of got the right trends. You can kind of see it heating up, cooling down, heating up, but there is huge steady state error, right? So again, this is one of the major problems of this type of control system, and maybe we should hop back to the board and let's talk a little bit more about this. All right, so I think we saw some benefits and some drawbacks of this type of a system. So why don't we take a moment to kind of summarize some of the pros and cons of this type of open loop control system. So on the pros side, I think obviously the number one reason why you might want to think about this is because it's simple, right? It's one table, or maybe it's a multi-dimensional table, but it's not complicated, right? It's a lookup table. It's effectively all you're implementing, right? So it's simple. The other thing that is attractive about this system, right, is because we are not feeding back the temperature, right, or the output signal, you don't need any sensors, right? Because your controller is not changing or switching its behavior based on this. So why even measure this, right? You don't need to purchase sensors. You don't need to implement anything. You can basically you don't even care what the system is doing, right? This is effectively the idea of closing your eyes and doing something and hoping for the best, right? That's what open loop control is doing. So you don't need a sensor, okay? Which makes it somewhat economical, right? Because you don't have to buy anything, right? So it's pretty darn simple. Also, because it's so simple, it has very low computational power required, right? You saw we implemented this on a very simple Arduino. There's no problem. You're not inverting any n by n matrices in this scheme, right? It's a lookup table, right? It's pretty much as dumb as it can get. So low computational power. And here at the bottom, I guess this is really just saying that you don't require any real advanced techniques to synthesize or to design this controller. I might want to put a little asterisk on this, and we're gonna come back to that in just a second. So maybe let's put a little bit of an asterisk right here in an orange color, and let's hit that in just a second. Okay, now there are some pros, but there are some big cons of this system, right? Number one is this system is not robust, right? We saw that earlier. Because this controller does not change its behavior, it doesn't care what is happening downstream. It does the same thing every time. If anything is wrong here, or if anything is different than how you modeled it or anticipated it, it's not gonna work, right? So not robust means this system, the plant, and on the environment, it better be exactly the way you designed it for. Otherwise, we saw it, you're going to have some potentially big problems happening. Okay? The other thing that maybe we should talk about, and we'll look at this soon here, is the response time might be slow. And maybe it might be worth just talking about that a little bit. Right? We saw here, if you wanted some temperature of like, I don't know, 53 degrees Celsius, right? We saw that this lookup table, it might cook up a duty cycle and say, okay, you need your duty cycle to be, I don't know, like, I'm making up these numbers, 42%, 0.42, right? So what's going to happen is that the temperature versus time, right? It's going to try to get up here to around 53, right? But it's going to do this slowly, because what this control signal over here is doing, right? If we were to plot this, it's just sitting here at 0.42. It's just flat, right? Because you're just basically looking up the steady state value. Well, this is kind of dumb, right? Because you know you're way too cold here. So initially, you should be cranking this thing up to 100%. You should turn on the heater as hard as you can until you start getting near, then maybe you're going to eventually at steady state you want a 0.42 duty cycle or control signal, but not initially, right? So you're paying this price here for the fact that this controller is so dumb and so simple that it doesn't think about any of this. It just says to get to a steady state temperature of 53, I need a steady state input of a certain duty cycle. So you're going to pay for that. And again, we're going to get around this in just a second in some of our next videos, but I just wanted to point that out, okay? So that's some of the pros and the cons. One item that I didn't write down here that kind of relates to this asterisk here is that sometimes you'll see this as a pro or a con. Maybe I'll write this again in orange. One thing to note is this system, when you talk about open loop control, a lot of times people are going to say this does not require advanced plant information, right? At the end of the day, we kind of just were looking at the steady state behavior of the plant, right? That's how we synthesized this lookup table and inverted it and did all of this stuff. The reason I'm not putting this as a pro or a con here is I think you could almost make the argument that actually the reason this thing is not robust is because you don't have some information about the plant. So really, in order for an open loop control system to work, you actually have to have perfect information about the plant and the environment. So I'm not sure if I can agree with this bullet all the time, but you're going to hear people talk about this a lot. They're going to be like, oh yeah, open loop control, you don't really need to know anything about this, the system, which is kind of true, kind of not, right? If you want open loop control to work, you actually have to have every bit of information about the plant and the environment. So you need perfect information about everything in order for this to work. In fact, this idea of requiring perfect information, that's actually the basis for some more advanced open loop control systems like feed forward control. And I remember earlier in the beginning of this discussion, we said this topic is just lookup table. This is almost like the dumb version of open loop control. There's way more advanced open loop control schemes, which sometimes fall under the moniker of feed forward control. And in that case, you do need a lot of information. And then this bullet also kind of goes out the window. If we're talking about doing advanced feed-forward techniques, you actually do need some advanced design techniques to synthesize controllers for that. But again, I think I'm getting ahead of myself. That's not part of this discussion. This is the really simple system where I think a lot of these green points hold, and I think this all makes sense. So I think that's all I wanted to talk about. We are going to now, in our very next video, talk a little bit about getting a little bit more sophisticated and maybe making a very simple closed loop control system to address some of these problems that we're seeing here in the open loop control system. But again, that's coming down the road. And like I said, also we'll have some future videos also talking about some of these feed forward techniques if you're interested in that as well. So with that being said, I think this is probably a great spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. It really does help me if you scroll down and click on that subscribe button. And remember, the new videos come out every Monday, so I hope I'll be able to catch you at a future discussion and we can all learn something new together. So until then, I think I'm going to sign off. Talk to you later. Bye.